co-chairs. And I'll let Sean introduce himself as the other co-chair for this session.
Yeah, hi, this is Sean Shi from University of Colorado. And yeah, so I think Stephanie will give will lead the session in the first half for the 10 minutes talk, or actually 8 plus 2 minutes, or this 2 minutes question and discussion. And I will take over for the lightning talk at the later half of the session.
Yep. Yeah, so just as an overview, we have around 6 of the longer 8-minute talks, and there will be 2 minutes for questions after those talks. And I will do my best to have a timer on in my background, so you can pin my window to your screen, or I can see if I can pin it. I don't know if it does anything. So you can be able to check that out, but I'll also give you a verbal reminder at the if you have 2 minutes left and then 0 minutes left when we have to move on. And then as Sean mentioned, after those 6 talks, there will be, I believe, 5 or so lightning student talks that will be around 2 minutes each. He'll give a reminder at the 1.5 minute mark. And then we have a longer discussion opportunity at the end where you can ask questions from any of the speakers that you heard from, so lightning talks and the longer talks as well. And so that'll be about 20 minutes to be able to do that. And so our session will end around 1 p.m. Pacific time. And you can, during the shorter discussion sessions, ask your questions in the chat, please. And if you could use a bracket and a capital Q to denote your question, that will help us to read it from the chat and get your question answered from the speaker. And then during the longer discussion session, feel free to use the raise hand feature if you'd like to be called on that way, or continue to ask your questions in the chat. And we'll just go back and forth selecting people to ask their questions. And we ask that you stay muted and keep your cameras off unless you're called upon by one of us. And then please, yes, respect the intellectual property rights of the presenters by not sharing screenshots of their work. And feel free, if the chat is too distracting, to close it, and we will try to make sure that anything relevant is verbally mentioned to you. And then there might be, I don't see it here. I guess it's not an option. But okay, so yeah, somebody asked what the aim of the poll was, and okay, that was answered already. Yeah, so just at the end during the discussion session, I'll put up those results for what people decided were their favorite asteroids. So we have 1 minute until our first scheduled talk by Dr. Hirabayashi. So I don't know if you are already available.
Hello, how are you?
Hello, let's see. And
do you want me to share screen or?
Yes, yes, that would be great. So I don't have access to any of the presentation materials. So
yeah, would you be able to give me permission for it?
Let's see. I'm not sure how to.
Oh, can you currently not share? Oh, sorry about that.
Yeah, it sounds like we can share. So I'm not sure how I give permission, or if you're able to give permission.
1 second. Sorry about
that.
Yeah,
suppose you can make all the presenter co-host of the session.
Yeah, I'm trying to see that. It's not giving me the option. That's strange. 1 second. Okay, should be good now.
Yeah, thank you. Can you see that?
Yes.
Okay, and then I'm going to make a presentation mode.
Perfect.
Can you see it right?
Yep.
Awesome. Let me know when I can start.
Sure, yeah, I'll just go ahead and introduce you, and then I'll add this virtual background timer, and then when that shows up, go ahead.
Okay, sounds good. Before starting my presentation, I like to mention that a couple minutes ago, like we had a conversation like favorite asteroid. I hope by this presentation, I hope you include the target of HIABSA-2 extended mission as a part of your favorite asteroids. So I hope that happens. But anyway, all right, so I'm going to start my presentation. My name is Toshi Hirabayashi. I like to thank Stephanie and Sean for inviting me to this session. I'm delighted to introduce my talk regarding HIABSA-2 extended mission. I newly added new co-authors, Yeji Kim and Ryota Nakano, my students who also contributed to this work. They actually have lightning talks in this session, so please stay tuned. Okay, so regarding the background of extended mission, when you look at the spin period distribution as a function of asteroid diameter, you can see very clear, interesting trends, especially when you look at the 200-meter diameter line. There is a clear transition. So if you look at the larger asteroids, you can see clear spin limit, which is around 2.2 hours. By this, we can consider these asteroids are rubble piles. On the other hand, if you look at smaller asteroids, they can actually spin faster. Because of this, we can interpret that they would be either rubble piles or monolithic bodies. Well, by rubble piles, I mean rubble piles with cohesion. Potential explanation of this distribution may be Europe effect. Another explanation may be impact-driven disruption. When you look at space exploration missions targeting asteroids or comet, you can see clear bias. So all of them targeted large asteroids and comets, but there's no space exploration mission targeting smaller asteroids. However, I want to emphasize that they are the most common object in the solar system, and then it is very hard to observe them by using ground telescopes and even space telescopes. So it is very critical to explore them directly. HIABSA-2 extended mission is a small body rendezvous mission that uses the already flying HIABSA-2 spacecraft. The spacecraft is currently flying without no critical issues. The mission is planned to continue until early 2030s. We have just started the mission recently. The rendezvous target is asteroid 1998 KY26. The shape is reported to be spheroidal. The equivalent diameter is around 30 meters. The spin period is 10.7 minutes. The tumbling mode has not been observed yet. The taxonomy is related to darker materials, including carbonaceous materials. Because of the fast spin, KY26 is expected to have unique geological and geophysical conditions. When you look at stress condition on the top right, you can see the stress field almost positive everywhere. By this, the body always experiences tension. However, if you look at the stress field, it doesn't go up to even 10 pascals. That means is that the structure can be supported by weak cohesion. This finding implies a potential structural condition, which is either monolithic structure or rubble pile with cohesion. I must say that Yeji is going to give a detailed analysis for this, so please stop by her poster. Loose materials may not exist in surface regions unless there is a cohesion. So if you can observe grains and pebbles on the surface, that indicates the existence of cohesion. Fractures, craters, and other geomorphological features correlate with this asteroid's evolution. Also, because KY26 is small, solar radiation pressure can easily perturb the asteroid's orbit. So the perturbation driven by solar radiation pressure may be around 40 kilometers 1 year after the arrival of this spacecraft. So this magnitude is much, much higher than the orbital determination uncertainty. So we would be able to determine this effect at high precision. The flyby target is asteroid 2001 CC21. The shape is elongated. The equivalent diameter is around 700 meters. Spin period is around 5 hours. The tumbling mode has not been observed yet. The potential taxonomy is L. I like to mention about the mission phases. So the first Earth swing-by operation was done in 2020, and then it was successful. After that, it will take 6 years for spacecraft to arrive CC21, and then it will fly by this asteroid. During that time period, it will conduct remote sensing observations. After that, the spacecraft coming back to the Earth to conduct another Earth swing-by in 2027. It will depart from the Earth, but coming back to the Earth again in 2028 to conduct the final Earth swing-by operation. After that, it will go to KY26 directly. During the long-term cruise phase, the spacecraft will conduct zodiacal light and exoplanet observations. I like to mention the Hayabusa 2 extended mission will contribute to exploring key planetary defense and science questions. Such key questions include: how do tiny asteroids exist in the near-Earth region and influence the Earth-Moon system? How do the most common objects look like? And how can we mitigate potential risks of these asteroids coming to the Earth? Finally, I want to mention that the spacecraft is definitely getting older, so it is necessary to monitor the spacecraft carefully. And we need a careful mission planning, but the extended mission team will continue to their best to explore these questions. By this, I want to stop my presentation and take questions. Thank you.
Great, thank you so much for that excellent talk, and it's really exciting extended mission opportunity. So we have a little under 2 minutes for any questions. Anybody wants to type something in the chat, or otherwise we could save it for the later discussion period. But feel free to start asking questions there. But I can start with a question. So what would this spacecraft potentially reveal about the asteroid that our current remote sensing capabilities are just not capable of showing us?
Say it again, please.
So what about this close flyby opportunity would we be able to learn that remote sensing from the ground, from the Earth, wouldn't be able to tell us about the asteroid?
Yeah, thank you so much for this question. Definitely, we will be able to get higher resolution images. So we plan to have visual camera imaging and spectroscopic analysis, and we have thermal imaging imagers as well. So we would be able to get higher resolution images, and we would be able to see very detailed geomorphology and surface conditions as well. So we are very excited to go there to see the details.
Great. I think Sean has a quick question.
Yeah, just very quick. Because of the fast rotation, I think it would be very challenging to, for example, characterize the thermal inertia. Do you plan, is this in the plan of doing so?
Yeah, that's a good question. We definitely assessing right now. So definitely the mass itself is very small. So first of all, it is necessary to understand the mass. And then in order to understand the mass, we need to characterize or plan, the location of the spacecraft. So what we have to do is to careful, the mission planning to be able to measure these parameters, given, the small bodies, like I said. Our mission plan that we have done for example, Ryugu, doesn't apply. So we need to do careful assessment. Well, thank you so much for this question.
All right, great. Thank you again. And any follow-up questions can be asked during our end of session discussion section. So up next, our speaker is Dr. Umberto Campins. He's on the science team for the OSIRIS-REx mission, and he will present his talk on exogenous material on Bennu. So Umberto, if you'd like to share your screen, and I will go ahead and start the timer when you're ready.
Okay, thank you. It's not allowing me. Huh.
You should have co-host abilities now.
Yeah, I know. Something is strange. I don't know why this is not.
You have to give permissions. You might have to exit and come back in.
Yeah, let me change computers. Can you go to the next person because it's not allowing me? Maybe
sure. If Joe DiMartini is available to give their talk, we can just swap the spots.
Yeah, I'm ready to go.
Great, awesome.
I just need, I also need the co-host permission. Ah, brilliant. Thank you. Okay, let's see. You can see my screen. You can hear me okay?
Yes.
Yeah, perfect.
Great, and I'll just start the timer now and let you introduce yourself and start your talk.
Thank you very much. Hello, everyone. My name is Joe DiMartini. I'm a PhD student at the University of Maryland, College Park, working with Professor Derek Richardson. Today, I'm going to talk to you about the influence of irregular grain shape on the Brazil nut effect in low gravity. This work was supported by the GEODES SSERVI mission. So first, a little bit of introduction. The recent missions to asteroids Bennu and Ryugu by OSIRIS-REx and Hayabusa-2, respectively, have shown that rubble pile surfaces can be highly complex, with such features as smooth versus more rough patches of terrain, indicating a large variability in the surface grain size distribution, as well as large boulders without associated craters, indicating possible vertical regolith migration. Both missions also measured approximately 50% bulk porosity on these asteroids. That is a 50% under density relative to if they were monolithic. And so one possible explanation for these large surface boulders I've singled out here without associated craters could be the Brazil nut effect. What I want you to imagine for the Brazil nut effect is that I've got a big jar of mixed nuts, and for argument's sake, all of them are equal density. The Brazil nuts and everything are sort of spread out throughout originally. And if I shake it up really hard, really vigorously, then after some time, the Brazil nuts, the largest particles, will rise to the top. This is true, we have shown this to be true in granular media, sort of in general, and the mechanism at work here is sort of what's called void filling, where shaking this up, the larger grains create these voids that the smaller grains sort of fill into, and it propagates up and up and up through the medium. And so one question that we aim to answer here is whether high porosity granular media create a more efficient Brazil nut effect. Higher porosity, more void space, possibly more efficient rise of larger intruders. And the way that we're going to investigate this is numerically. We use the parallel n-body gravity tree code PKD-grav, which uses a soft sphere discrete element method to model contacts between spherical particles, allowing for very slight interpenetration of the spheres at the point of contact as a proxy for surface deformation, and with the degree of interpenetration mediated by a restoring spring force. This approach also allows us to model rolling and twisting, as well as sliding friction, and normal and tangential restitution between our spherical particles. Now, recently in PKD-grav, we have gained the ability to efficiently simulate large numbers of irregularly shaped particles using what we call aggregates. Essentially, we glue together a couple of spheres into an irregular shape. And this is great because suddenly we gain the benefit of being able to model shape effects in a granular medium, but we maintain the relatively simple calculations for spherical gravity and sphere-sphere interactions. And the importance of being able to simulate with aggregate particles has to do with the porosity of granular media. I mentioned before, Ryugu and Bennu were measured to have approximately 50% bulk porosity. And the most efficient packing distribution for monodispersed spheres is the hexagonal close pack, which you can see in this image up here from my 2019 paper. And this has about a 26% porosity in a medium of monodispersed spheres. We can then move to a slightly less efficient packing distribution. We have a random packing of spheres that are all different sizes, and we get somewhere around 50% porosity. And you can see that here in one of our collaborators' recent publications. But when we make a medium of mixed aggregate particles, irregular shapes, we've found that we can get up to 70 or even 80% porosity in the medium. And this is great because in the OSIRIS-REx tag sample return in situ experiment, the tag arm penetrated like a half a meter deep, like a half a meter deep into the regolith layer, indicating potentially very high porosity, much higher than the 50% bulk porosity number. And this is reasonable because you can imagine at the surface, there would be a lot less overburden pressure than deeper down in the asteroid. So on to our actual experiments here. This is the way that we set up our simulations. We have a sort of periodic box. We have periodic boundaries. And we have a large red Brazil nut aggregate down at the bottom here, which is approximately the same density as the medium around it. We then drop these aggregate particles down around it so that they can pack sort of randomly around the Brazil nut. And we do this for all 5 of the aggregate shapes that you see up here, as well as with single spheres for comparison. And we do analogous simulations turning such toggles as interparticle friction, which has been shown to be an important factor in the rise speed of the Brazil nut particle, interparticle cohesion, Brazil nut size ratio, the ratio of the Brazil nut to the size of a typical particle in the medium, as well as the strength and style of the shaking of the medium. So let me exemplify this with one of our earliest simulations here, where basically we have this box full of particles, and you'll see the Brazil nut come up in just a second. It's the only red particle in the simulation here. And we basically give all of the walls a sinusoidal oscillation with amplitude and frequency chosen such that the equivalent acceleration is 3 times that of the ambient gravitational acceleration. This is a Froude number of 3, as it were. And we measure the height of the Brazil nut as a function of the number of oscillations. So this red dashed trace that you're seeing here is the Brazil nut height during the simulation. The blue dashed trace is the median height of a particle that is not the Brazil nut in the particle bed. And this black dashed line indicates the initial height of the particle bed. So when the Brazil nut reaches approximately this black dashed line, it has reached the top of the medium. Our more recent experiments, as I showed before, have been using periodic boundary conditions. And these are ongoing, but you can tell just from this figure in comparison to the last one that it's a little bit more difficult to interpret the results. I believe if we simulate this for just a little bit longer, that the Brazil nut comes up to the top and sticks there. So this is the work that is ongoing. In addition, we have a different method of shaking. So rather than just those sinusoidal oscillations on the walls, we can use acceleration data from a seismometer about 150 kilometers from one of the artificial impacts on the Apollo 16 mission. And we can scale the magnitude of that acceleration to simulate being closer or further from the impact site. And so you can see here, we sort of do repeated shakes with different magnitude accelerations to say, oh, we're much closer this time, further this time. I'm starting to run out of time, so I'll go to my conclusions here. One of our main findings is that systems of irregularly shaped grains produce much more porous media than systems of discrete spheres. And to that effect, we find that simulating shape is very important for accurately modeling the Brazil nut effect. Here is just a quick grid of our initial results for some of these simulations with irregularly shaped spheres, particles in the Brazil nut effect. And we find that in most cases, the Brazil nut rises to a taller relative height and more quickly than in simulations with only spheres. We are also in the future working on simulating the sound speed of through granular media with impact experiments compared to similar laboratory experiments. I think I'm out of time here, so thank you very much and happy to answer any questions.
Great, thank you so much. And modeling granular media is near and dear to my own heart, so it's always nice to see. So yeah, as usual, feel free to use the chat box if you have any questions. I think I see a hand raised by Antara, if you'd like to unmute.
Sure. This is actually really interesting, and it's relevant to something we're studying right now. So I had a question. So on Bennu, we're seeing this dichotomy of boulders with different densities and as well as different porosities. So given the results that you're seeing right now, which look quite promising, do you have any predictions for what the implications of different densities might be?
Yeah, so for the Brazil nut effect, for the most part, we find actually that density is not a huge factor. It's possible that when your large particles are significantly underdense compared to the particles in the medium, that you actually get what's called the reverse Brazil nut effect, where the larger particles actually move down lower, which is sort of the opposite of what you would think in terms of like buoyancy rules, right? The less dense thing should rise, the more dense thing should drop. But there's a lot more work to be done about that. But the different densities, that's really interesting. And depending on, the proportions of different density material on the surface, that could be interesting to look at. Sorry, I don't have a better answer for you.
All right, yeah, thank you so much. And we're out of time for this section of the discussion, but there are a couple more questions for you, Joe, in the chat. So if you wanted to go ahead and respond to those in your own time. So our next speaker is going to be Dr. Campines. So let me change my background.
Thank you, Joe, for bailing us out on this.
Hopefully you can share your screen now.
Yep.
Yes, awesome. Perfect, all right. So I will go ahead and start the timer and you can start your presentation.
Okay, thank you, Stephanie. And so today I'm going to be telling you about more exogenous material on Bennu that we have discovered by using the MapCam and Polycam images on OSIRIS-REx. And this is work in collaboration with Eri Tatsumi, Marcel Popescu, Juan Luis Rizos, Amy Simon, Hannah Kaplan, Danny De La Justina, Julia De Leon, Javier Licandro, and Dante Lauretta. And here's a quick outline of my talk. I'm going to be giving you a little bit of background on the material that has already been published, reporting exogenous material on Bennu by De La Justina et al. 2021 and by Tatsumi et al. 2021 on Ryugu. The new candidate, then I'm going to be telling you more about the new candidate exogenous material that we have identified on Bennu. So in addition to the 6 exogenous boulders that were identified by De La Justina et al. 2021. We have 71 additional boulders identified because of their red slope and absorption near 0.9 microns using MapCam colors. And we find that there are at least two compositional types. One that is consistent with mixing HED material with the average Bennu material, and the other one that is consistent with mixing ordinary chondrite type material with the average Bennu material. And then I'll tell you a little bit about the conclusions. So as I mentioned, De La Justina et al. 2021 used albedo, color, and spectra of 6 bright boulders on Bennu that were very distinct from the rest of the surface and that are likely basaltic material specifically from Vesta. And then Tatsumi et al. 2021 identified bright boulders on Ryugu that show absorptions near 1 micron, but not near 2 microns, suggestive of olivine-rich anhydrosilicates consistent with ordinary chondrite material. And so here are the 6 boulders identified by De La Justina et al. 2021 on Bennu. I'm not going to go too much into this, but I will tell you more about what we've done. So since that publication, we have identified 77 bright boulders on Bennu using the MapCam and Polycam images. And these have red spectral slopes, and the average Bennu has a blue spectral slope. And these also have significant X-band, which is centered at 0.85 microns absorptions. And so our 77 boulders that we identified include the 6 that had been identified previously by De La Justina et al. And we find that these are scattered throughout the surface. We limited ourselves to latitudes below plus and minus 70 degrees on the surface of Bennu. So here's the plot on the latitude, longitude. And the next one is a plot on the actual global map of Bennu. And our exogenous candidates tend to be in areas with larger average size. So, but that's just part of the preliminary results. Here are some images of our boulders. So we find them either as single homogeneous boulders like this one. We find them as pieces of a larger boulder. And we also find them as breccia type material that are, basically bright objects encrusted into a matrix of darker Bennu-like material, average Bennu-like material. We find no correlation with between morphology and spectra, but we do find 2 distinct spectral mixing trends with respect to average Bennu. One of them can be explained by mixing HEDs and Vesta material suggested by De La Justina et al. 2021, and the other one by mixing the average Bennu with olivine-rich anhydrous silicates. So those may explain these at least 2 different compositions of the exogenous material that we have identified. In addition, the near-infrared spectra using the OVIRS instrument on OSIRIS-REx also support multiple compositions among the exogenic objects on Bennu. So we have both color and spectral evidence of more than one composition of the exogenous material on Bennu. Now, the comparison with Ryugu, which was done very nicely by Tatsumi et al. 2021, indicates that Bennu is about 40% more abundant in exogenous material. I mean, not 40%, 40 times more abundant in exogenous material than Ryugu. And so this likely reflects differences in impactor velocity, size, composition, the environment in which the collisional evolution of these 2 objects occurred. So the exogenous material can constrain the collisional history of each of these 2 objects. So in conclusion, we have exogenous material that has been identified on both Bennu and Ryugu, and we have done in this work further analysis on Bennu using MapCam and PolyCam images, and we found a wider diversity and many more examples of this exogenous material. So we are expanding on the findings of Della Justina et al. 2021. We continue our study of this diverse material on Bennu and Ryugu to constrain their origin, their evolution, and their collisional history. Remember that the average collisional velocity in the asteroid belt is supposed to be, it is 5 kilometers per second, and the outcomes of such collisions would not leave any of the impactors surviving. So there's something that we're missing in our models of collisional evolution of these objects, and also that the return samples could contain the exogenous material. So we are excited about having samples not just from Ryugu and Bennu, but from these exogenous materials that are on them. Thank you. I'll take any questions.
All right, thank you so much, Humberto. So if anybody has a question, please feel free to type it into the chat box. I had a question. So in Joe's talk, he had mentioned that these boulders didn't have a crater associated with them and that they were sort of brought up from the surface. So are these exogenous materials thought to be delivered by an impactor or some other process?
Definitely impacts, and it is not clear, as discussed in both the Della Justina et al. And the Tatsumi et al. Papers of 2021. It is not clear if the impacts occurred on Bennu and Ryugu. It is more likely that they occurred on their parent bodies. So that is much more likely to yield the survivability of these large boulders. Good question, thank you.
Okay, we have a question in the chat from Antara, and they ask, are the spectral signals of exogenous materials similar? Are there predictions for the composition of these materials?
They're different. Based on just the colors, which is what we've done, it's clear that there are two trends. One, which would be mixing average Bennu material with HED meteorites or with Vesta type material, and the other one would be with ordinary chondrite meteorites. And it's interesting that on Ryugu, they have found no evidence of Vesta-like material. So Bennu and Ryugu are different. Bennu contains Vesta-like material and ordinary chondrite-like material on the surface. Ryugu contains only ordinary chondrite-like material on the surface as exogenous. But we are, this is only our second phase. First was the discovery. This is our second phase of our study of these objects. We're going to be doing a lot more and hopefully identifying more details about that diversity. But on Bennu, at least two types of exogenous material have been identified.
Okay, great. And we're running a little bit behind, so we're going to go on, and thank you, Humberto, for your
Not because of me.
No, not because of you. So we're going to move on to Shang-Chi's talk, fellow co-chair. So if you would like to share your screen. All right, and then I will change over to the timer, and you can go ahead whenever you are ready.
Hi, this is Shang-Chi, and I hope you can see and hear the presentation well. That I'm presenting a recent modeling work by me, Xu Wang, Anthony Carell, Noah Hood, and Mihai Horani about the grain size evolution of on asteroids. And the main motivation, as some of you have seen previous version of this presentation, is that the motivation is we try to understand what causes the diversity of these different sceneries on these bodies. As you can see on the moon, we have very dusty surfaces, and moving to smaller bodies of like the Bennu and Ryugu, which recently explored by these excellent sample return missions. And these worlds are tiny and dominated by, and the surface is dominated by boulder fields. And that's why we are thinking in the way like how this is, what are the processes shaping the surface.
Oh, you're muted, Sean.
here we go. Sorry. Yeah, I just muted myself. And the way of thinking, of course, we can follow an analog we have on Earth. That along the shoreline, the conditions could be different just from the very short different distances. That depends on the in situ conditions that we could consider very different process that will determine how the shoreline will look like. For example, we could have transportation processes that, for example, bring the sand from these rocky shores and deposit it into the more stable regions and form a beach. You can also consider the fragmentation process that bring down and change the size distribution. And so for asteroids, we consider three processes to be the key players. Starting from the left, we have thermal fragmentations, which has been simulated in the lab and also observed on Ryugu and Bennu, that this could be a major fragmentation or process that break down the border into smaller pieces. And we can also have, of course, impact processes that produce fragments, and depends on the escape speed of the body, how much it can retain its materials, and we can have a removal process that, in contrast to a thermal fragmentation, it will remove material, likely smaller pieces from these bodies. And lastly, we also consider electrostatic dust transport process, which is modeled in the lab, as you can see, by shining electrons and UV lights. These ionizing radiation will produce a different charge on the porous regulars and allow charge to accumulate and repel when sufficient to repel each other and produce this transportation kind of hopping motion of particles with a speed roughly lower than a meter per second. And some of you might hopefully remember what we presented last year is that because of the small gravity of small bodies, that we show that for asteroid at 1 AU or nearest asteroids at 1 AU heliocentric distance, that below 1 kilometer of the radius, they don't have gravity enough to retain materials losing by electrostatic lofting. And so for that, we predict that smaller bodies will be basically fine-grained material free, and that is consistent with what we see. And the progress we made this year is that we not just derive compare the rate of fine-grained material production, but we also expand to model the size distribution of the system, of the regular system on asteroids. And the same, we consider these three different processes working together that shape the size distribution of asteroid regulars. And of course, on the left, you have thermal fragmentations that basically doesn't change the system mass, but bring down masses from larger particles into smaller particles. And of course, we have impacts that produce fragments and depends on the gravity. For small bodies, most of the ejecta can escape. And we also have the electrostatic dust lofting that basically only operate in the mass budget terms that only affect the smallest particles, which of course depends on the size of the body, on the extent of these effects. And putting all these together, we have this very busy time evolution. On the top, you have the size and the surface area distribution of the regulars on these 500-meter radius hypothetical asteroid located at 1 AU. And we start with a rather steep size distribution of with an index of -3.5. So at the beginning, actually, most of the surface, about 90% of the surface is covered by grains smaller than 100 micron. But with time, and because of this prevalence of small particles, electrostatic lofting is the most important process at the beginning, as you show from the bottom plot, shows the rate of various process. And you can see in the first few thousand years, electrostatic lofting remove a lot of fine-grained materials and start to shaping the size distribution, at least in the grain size below 22 microns, which is the range can be affected by electrostatic lofting on a 500-meter body. But with time, with the losing of fine-grained materials, you lose the protection of these material to the larger grains. So they are more and more exposed to space elements, and their erosion start to pump up, and you can see the fragmentation rate start to increase a little bit, experiencing a bump, kind of a minor increase after 10,000 years. And that's because the more exposure of these larger grain populations and the more effective they are being eroded. And therefore, by introducing to the electrostatic forces, you not just change the smallest population, but you introduce this coupled size distribution evolution. And if we want to bring up the contrast that this is on the right shows the case for much larger objects with a 5 kilometer radii. And you can see that the electrostatic forces only affect, only be able to remove particles 2 micron or smaller. And that means electrostatic lofting is actually a minor process here, and the dominant process is fragmentation. And you can see after 10 million years, more than 50% of the surface is covered by micron-sized grains, in contrast to the small ones, where after the simulation of the same period of time, that 50% of the surface should be covered by grains larger than millimeter. And we can also simulate a lot of different cases, basically using a Monte Carlo approach to sample the different combination of the initial parameters as shown here. And we see that at different, for grain, for parent body or asteroid size radii from 100 meter to 10 kilometers, it's basically a linear relationship between the time where the fine grain material is depleted, which is defined by that more than 50% of the surface area is covered by grains 500 micron or larger in radii. Or in another way is that these smaller grains cannot form a uniform, if they distribute uniformly, cannot form a monolayer covering larger grains populations. And so it seems that these processes are actually quite effective based on the parameters we considered, and small asteroids, as you can see on the left upper part plot, that asteroids smaller than 1 kilometer are more likely, more than 50%, to form to be depleted in fine grain regulars. And this is the summary slide that basically we consider 3 processes as discussed, and the key or the kind of the new elements is the electrostatic lofting that removes small particles and only effective on very small bodies. And the size distribution we derive is roughly consistent with the in situ measurements reported from OBSERVATORY-Rex and Hayabusa 2 missions. And also what I want to stress is that by losing fine grain material, you also change the thermal properties of the surface, which could mean that it has implication to the orbital evolution or the surface spectra characteristics for small asteroids. And thank you for your attention, and I take questions.
All right, thank you so much, Sean. Unfortunately, we're out of time for the discussion, the little discussion section at the end of your talk, but we can, any questions that you have for Sean, you can enter them into the chat or save them for the longer discussion period at the end.
Sounds good, thank you.
Okay, so next up, we will be hearing from Lauren McGraw, and I believe, let's see, I think Michael will be sharing their screen. Let me change.
Yep, just one moment.
Yeah, no problem.
Hello, everyone. Today I'm going to talk about OH and H2O characterization of near asteroids using three-micron spectroscopy. This is the culmination of about 5 years of
Or is it a pre-recorded presentation? I guess
observations of NEAs. And so I'm going to show you our end results and conclusions thus far. The motivation for this project was to learn more about the OH and H2O content of near-Earth space And it was previously thought that objects in near-Earth space that didn't have atmospheres would be nominally anhydrous because of their increased temperature at formation and their low perihelia. However, in 2009, multiple missions discovered a 3-micron feature on the moon, and in 2012, discovered a similar feature on Vesta. On the moon, the 3-micron feature is believed to have been caused by hydrogen implantation due to the solar wind, but on Vesta, it's believed to be from carbonaceous material influx. In 2018, Rivkin et al. Determined that the 2 largest NEAs, Ganymede and Eros, also have a 3-micron feature, and the delivery of that material was also likely due to the solar wind. For our project, we used IRTF SPECS near-infrared spectrometer, both the PRISM and LXD short mode. We conducted 43 observations of 29 NEAs, so we have multiple observations of several of our targets. After observing and downloading the data, we process the data using the SPECS tool package, and then we use a NEDM to remove the thermal tail. So in this plot on the right, with reflectance versus wavelength, the black data points are the original data, the blue are the thermally corrected data, and the red line is the reflected continuum. For this particular asteroid, 2000 WO107, it does not have a 3-micron feature because the blue data points lie along the red reflected continuum in the 3-micron region. So this asteroid does not have OH or H2O on its surface. However, we've determined that 4 of our asteroids do indeed have a 3-micron feature. Ganymede and Eros were observed in this project as well, and were also seen to have a feature just like in Rivkin et al. We also determined that 3122 Florence has a feature. And most recently in 2020, we observed 1999 AP10 and determined that it also had a shallow feature in the 3-micron region. We also have several NEAs with a potential 3-micron feature. These objects have a higher degree of noise in the spectra, but if you use a 2 sigma error, you can see that the band is still there. So 1627 IVAR, 2004 JN13, 2014 JO25, 1998 XB, and 2002 PZ39 round out our collection of NEAs that look to have a 3-micron feature and OH or H2O on their surface. So the next question is, what drives OH and H2O delivery and retention? If it is the solar wind delivering H ions and creating OH and H2O on the surface, one might think that all of the NEAs studied would have these features. However, that's not the case. So something must be controlling the delivery and or the retention of this material. One thing that we determined after processing all of our data is that there are multiple band shapes in our collection. So band shape type 1, which is exhibited by 3122 Florence, 433 Eros, and 1627 Ivar, is a wide linear feature similar to the sharp feature discussed in Takir and Emery, 2012. These asteroids are all about 4.5 kilometers or larger in diameter. Their perihelia are greater than 1 AU, and they're all S-types. We believe that the volatile composition is pure OH, as a sharp linear feature has been confirmed to be due to OH on multiple other papers. And these objects, we believe the solar wind delivered this OH delivered the H to make OH via hydrogen implantation. Band shape type 2 is possessed by 4 NEAs, 1999 AP10, 2014 JO25, 1998 XB, and 2002 PZ39. These NEAs have a narrow and flat feature compared to the sharp linear feature of the previous NEAs. These NEAs are all less than 2 kilometers in diameter. Their perihelion is about 1 AU or less, and most of them are Q-types or something similar. JO25 is an SR type, so it doesn't quite fit the same compositional trend as the others. We believe the volatile composition present on these asteroids is a mix of OH and H2O potentially, as a more bowl-like feature seen in Takir and Emery 2012 is indicative of the presence of H2O. So we believe this might be a mixture of the 2 materials. We think that to some degree, solar wind hydrogen implantation is still the main cause for this feature, but another process such as recombinative desorption might be forming water at high temperatures when these objects are near perihelion. Finally, the third band shape is possessed only by 1036 Ganymede, and this is considered to be a wide flat or bowl-like feature. Ganymede is an SR type with a very large aphelion of 4.08 AU, which means that it easily reaches into the outer main belt of asteroids. Interestingly enough, when compared to a spectrum of Vesta taken in this study early on, we see that the band shapes are actually quite similar. So we believe that the delivery mechanism might actually be similar as well. So we think that Ganymede likely has a 3 micron feature due to the influx of carbonaceous material on its surface. And being that it can go all the way into the outer belt, this seems likely as well. In conclusion, we've observed 29 NEAs, and 4 of those have a feature, and 5 potentially have a feature. That leaves 20 other NEAs, 9 of which do not seem to have a feature, and 11 have too low of signal to noise ratio to really make a determination. We have 3 band-shaped types that seem to indicate something about where the OH or H2O came from. Type 1 is composed of large, high-Q S-type NEAs, and we believe the OH is from the solar wind. Type 2 is composed of smaller, lower Q NEAs, and seems to have a mix of OH and H2O from solar wind hydrogen implantation. And finally, type 3 are possibly V or R type NEAs, such as Ganymede, that have OH and H2O from carbonaceous material influx. Thank you very much. Please feel free to email me if you have any questions or discussion points. I apologize that I couldn't be here in person to field your questions, but I would love to talk to you via email or some other mode. Thank you again.
All right, great. I don't know if she included her email in that presentation, but I can do my best to find that and post it into the chat so that you can direct any of your questions from that presentation directly to her. So we'll move on to our final of the longer talks before the student lightning talks. We'll hear from Vanessa Lowry. So if you're ready, let me change this. All right.
Hello, can you hear me?
Yes. Are you ready to go ahead and give your presentation?
Yeah, I'm ready.
All right, I will start your timer then and you can go ahead.
All right, thank you. Hello, everyone. I'm Vanessa Lowry from the University of Central Florida. I'm giving my talk to you today on my recent work on T-matrix and half-key modeling of thermal infrared spectra of the Trojan asteroids. I have my co-authors listed right underneath the title, and I am currently being advised on this work by Carrie Donaldson-Hanna. All right, just a brief slide about the background and motivation as to why we should study the Trojans. The Trojan asteroids are 2 populations of asteroids that reside 60 degrees in front of Jupiter's orbit and also 60 degrees trailing behind Jupiter's orbit. This plot that I'm showing you are spectra obtained by the Trojans are highlighted in red, and those have been obtained by Dr. Joshua Emery using the Spitzer Space Telescope in 2004. And I'm showing this plot in order to emphasize the prominent 10 micron plateau, which is not a unique spectral feature. This is also shared between other solar system bodies. Cometary spectra have this feature, as well as other asteroids like 944 Hidalgo that I showed there in the bottom panel. In this work, I wanted to see whether we could model using widely spaced fine particulate olivine to explain the Trojan features. This is not an original idea. This was previously proposed by Emery et al. In 2006 as the cause of the 10 micron plateau. And also with cometary come-like porosities. Although this is not the first attempt in trying to model the Trojan spectra, there have been attempts in the past, although I do not, to my knowledge, this is the first attempt to model using varying particle sizes and varying regolith porosities. So a quick slide about my methods before I get to the results. So in this study, I used T-matrix, multispheres, T-matrix, and Hapke reflectance models. Those are light scattering and reflectance models. I have shown two graphics under there giving you an example of what the input is required for T-matrix, being the optical constants, where I have phthalate, which is iron-rich, olivine optical constants shown there, and also my particle positions. So with T-matrix, you're able to specify your XYZ positions of your particles. So this is a good thing because I can adjust the porosity to whatever porosity that I would like to model. This makes up the bulk rectangular target. So I did this full process of modeling for 21 minerals, 21 separate minerals, and this number does not count 4 different porosities within each mineral, and also varying particle sizes too. So I made a huge big library of spectral library of individual minerals to see which one, and I plotted each one and did a chi-square minimization to see which porosity was selected. So I originally fit each one individually to see which individual mineral would show the best fit. I then used a smaller subset of the spectral library to use the weighted least squares, excuse me, to fit the Trojans. However, I had to go back and redo the modeling because the weighted least squares is not appropriate for fine particles or nonlinear spectra. It's appropriate for linear. So once I got the result from weighted least squares, I went in and redid the modeling to give what is I call my final result. And onto the results. So this is 911 Agamemnon, and I used the NEDA model to fit the spectra to obtain the emissivity spectra. 911 Agamemnon is a D-type asteroid, and this asteroid lies in the L4 Lagrange point. So this is 60 degrees in front of Jupiter's orbit. I show the spectra in gray, so the measured in gray is the asteroid spectra with the model overplotted in blue. For this asteroid, the final result of the best fit, meaning the lowest RMS error. So what I did was, after going back and redoing the modeling, I would iterate and add more or less of phthalate force to right to find which one, using the T-matrix Hapke, not using the weighted least squares, would give me the lowest RMS error. So for 911 Agamemnon, the 0.5 particle radii size fit the best with 100% abundance and an overall bulk porosity of 75%. The next asteroid I modeled was 624 Hector. This asteroid is in the same group L4 as 911 Agamemnon, the last asteroid on the last slide. Both were fit with the 100% phthalate at the 0.5 micron size. With this one was fit with the 70% porosity, so very similar to the last asteroid. So this could possibly suggest a compositional trend among the L4 group. However, a lot more observations and modeling is needed. And then the last asteroid is 1172 that I modeled using these methods. This asteroid is in a separate group from the last two. This one is in the L5 Lagrange point group, so 60 degrees trailing Jupiter's orbit. This favored the 1 micron particle size and the 0.5 for Troy light. And you might be wondering why I have the 1 and the 0.5. So if an individual mineral fit the Trojan spectra especially well, I ran multiple particle radii to try to fine tune it. So this one favored the phthalate and forsterite. The bulk porosity here was, I have underneath in this table highlighted in yellow the porosities that I came up with using the weighted least squares originally. So then I averaged those 3 porosities to get the bulk porosity of 80%. So for this one, we believe that possibly that some intermediary olivine between the iron-rich and the magnesium-rich olivine would fit this spectra. However, to my knowledge, these obstacle constants are not available. And then the troilite was picked up by Aeneas. As you can see, the 12 micron sharp peak in emissivity is a little more smoothed out on this one. And also Aeneas has a more rounded 10 micron peak compared to the other 2 asteroids. So in conclusion, I broke this up into needed and not needed to be able to model the Trojan spectra. What was needed was mixture of iron-rich and magnesium-rich olivines, or one or the other. Also, we needed lunar-like porosity, so around 70 to 80% bulk porosity. What was not needed, that was previously proposed, was a fine particles of olivine embedded in a transparent matrix such as a salt. This was not needed. And then no ultra-high cometary Comé-like particle separations were not needed either. And that concludes my talk. And here's my email if you would like to contact me for any further questions. And thank you very much.
All right, great. Thank you so much, Vanessa, for a great talk. I really liked all your use of visuals there. It was great.
Thank you.
So we do have a minute. If anybody would like to ask Vanessa a question about her work that she just presented, you can feel free to type it into the chat. It's a little bit difficult for me to see raised hands in this format. But since we're kind of running out of time, I might just hand it off to Sean to introduce the next lightning talk speakers. And then if anybody has a question for Vanessa, please ask it in the discussion section at the end of this. And thanks again, Vanessa.
Thank you.
Yes. Thank you both. I think that went pretty well. So let's move on to the next half session. Next half of the session, and let's start to welcome Yeji Kim to talk about structural conditions of asteroid 1998 KY26, the new target of Hayabusa 2 extended mission. You have 2 minutes.
Okay, can you see my screen? And can you hear my voice?
Yes. Can you hear me? Oh man. Can you hear me?
I can hear you, but your video cut out.
We can see your screen. You can go ahead.
Yeah, you can go ahead. Kim, I don't think we can see your screen anymore.
Hello?
Can you hear us?
Yes, I can hear. I'm sorry. I'm gonna share my screen. So can you see my screen?
Yeah, we can see it.
Yeah, I'm sorry. So hi everyone, my name is Yeji Kim. I'm a first year PhD student and working at the START Lab at Auburn University. So it's a Space Technology Application Research Lab. My poster's title is Structure Condition of Asteroid 1998 KY26, which is the new target of Hayabusa 2 extended mission. So the co-author of this work is Dr. Hirabayashi. He was actually the first speaker in this session and presented Hayabusa 2 extended mission. So following his talk, in my poster, I'm going to introduce more details on the FEM technique that we used to investigate the stress field of KY26 and how to conclude that KY26 is still possible to be a rubble pile asteroid. Actually, this FEM technique is also applicable to any irregularly shaped bodies for structure analysis. So if you are interested in our simulation stuff and want to discuss KY26, then please visit my poster. My poster is tomorrow from 10 a.m. to 11:30 in poster session 2. So you can come to poster number 5 in the asteroid section. Thank you.
All right, great. Thank you so much. I think Sean is back. So I can
Yeah, sorry about that. So let's move on to the next speaker. Next, we have Marina Germa, and please go ahead.
Okay, if everybody can see my screen and hear me, I will get started. So my name's Marina Germa. I'm a PhD candidate at Columbia University, but I do my research at the American Museum of Natural History. And my dissertation work broadly focuses on the spectral and geochemical properties of meteorites. But today I'll be talking about my poster, which is poster number 7, titled Evaluating Mineral Variation and Metal Coarsening Across Petrologic Types of H-Chondrite Meteorites. So quantifying representative mineralogy in meteorites often involves destructive techniques, which sacrifice petrographic context in the sample. And to determine characteristic mineralogy for my H-Chondrite samples, I combine the non-destructive methods of 3-dimensional computed tomography with 2-dimensional X-ray mapping of sample surfaces. And so I examined trends in mineral abundance, variability, and coarsening of opaque assemblages or metal and sulfide phases across petrologic types of H-Chondrites. And we were able to not only preserve the petrographic context in each sample, but also assess the phase relationships of these opaque assemblages and the associated coarsening with petrologic type. And this precise characterization of mineral variability and metal coarsening across petrologic types of ordinary chondrites, in particular samples with high metal to silicate ratios, like the H-Chondrites, will provide valuable context and insight into the investigation of small bodies with high metal to silicate ratios, such as 16 Psyche. So if you're interested in hearing more about this work, you can visit my poster tomorrow in the poster session number 2, and I'm poster number 7. So thank you.
Thank you, Marina. So let's move on to the next lightning presentation by Ziris Sacha. Sorry for my presentation. Please go ahead. Ziris,
okay, can everybody hear me and see my screen okay?
I cannot see your screen, but I can hear you. I can see it now.
Okay, perfect. Okay, hello and welcome everyone. My name is Ziris Sacha and I'm an 11th grade high school student from St. Mary's School in Oregon. What if we told you that Vesta could have transient water flow on its surface? As part of LPI's Xmas program, our team researched the potential evidence for water on Vesta by comparing the geomorphology of debris flows in craters on Earth, Mars, the Moon, and Vesta. Prior to the Dawn mission, Vesta was believed to be predominantly dry and lacking volatiles. However, images from Dawn revealed evidence of fluvial debris flows in Vestan craters. Based on that data, we wanted to address whether Vestan debris flows exhibit morphologies consistent with wet debris flows found on Earth and Mars, and whether evidence for the influence of the liquid is present on Vesta. From our observations and comparisons of images from the Moon, Mars, Earth, and Vesta, we found that all 4 of these bodies share similar styles of mass wasting. When we observed dry flows compared to wet flows, we noticed 2 main differences: texture and flow direction. Wet flows appear smoother as a result of liquid mobilizing the materials, while dry flow tends to move straight downhill, and wet flows are curvilinear. Based on the similarity of wet flow geomorphologies on Earth, Mars, and Vesta, we found compelling evidence that several Vestine craters contain debris flows formed in some combination with a liquid. If you want to learn more about our findings, please stop by our station in Session 2, Asteroids Poster Rate, on Wednesday, July 21st from 10 to 11:30 a.m. Pacific Time. Thank you so much for listening.
Thank you. Very good. Let's move on to next speaker, Katarina Slavinska.
Can everyone hear me okay?
Yep.
Yes, I can hear you.
Okay. So hi, my name is Katie Slavinska, and I work for Dr. Christopher Bennett at the University of Central Florida. But today I'm actually dialing in from the University of Lille in France, where I've been working with Dr. Claire Perrin for the past couple months on a project analyzing carbonaceous chondrites with high-resolution two-step laser mass spectrometry, or L2MS. So L2MS is a soft ionization technique. It utilizes one laser to desorb species off of a surface and a second laser to ionize them at very low fragmentation. And at certain wavelengths, this technique is highly sensitive to polycyclic aromatic hydrocarbons, or PAHs, and it can be used to compare their relative concentrations in different meteorites. So in this poster, we used L2MS to compare the PAH size distributions and degrees of alkylation between 5 CM2 carbonaceous chondrites that have experienced various degrees of aqueous and thermal alteration to investigate the relationships between PAH inventories and parent body histories. So these studies show a possible correlation between the degree of alkylation of naphthalene and pyrene specifically with aqueous alteration. And additionally, we have been working on tuning this technique to map pH distributions on a micron scale and correlate them with other surficial properties like mineral distributions and peak metamorphic temperatures. So if you're interested in hearing more, my poster is number 10 in the asteroid room tomorrow, so please drop on by.
Oh, sorry, I'm muted. Thank you, Katie. Let's move on to the last but not least presentation, Roya Nakano. Please go ahead.
All right, let me just share my my poster. Can you see it?
Yes.
All right, so my name is Ryota Nakano. I'm a PhD student working with Toshi Hirabayashi at Auburn University. So in the poster, I present a thermophysical model, which we recently developed. The model uses a finite element method approach to solve three-dimensional heat equation. So it can describe very detailed thermal conditions of airless bodies, such as asteroid, comets, as well as local topographies like moon's craters or asteroids' borders. In this work, as an example, we applied the model to asteroid Ryugu and calculated the thermally induced torque known as the yoke torque. We found that on a specific epoch we looked at, Ryugu may have experienced the yoke torque that accelerates its spin, which is very interesting because Ryugu is considered to be spinning down. So lastly, I just want to note that I am actively improving our technique. So if you have any suggestions or questions, please stop by my poster. I would like to have discussion with you. My poster session is tomorrow at 10 a.m. The poster number is number 6. That's all. Thank you very much.
Thank you. All right. So we are entering the discussion phase. So if any of you have questions to the presentation or including some of the lightning talks, which could be questions for tomorrow's discussion at the poster session, you're welcome to either post in the chat box or unmute and ask. But do you want to share some results on the Mentimeter, Stephanie?
Right, yeah. I just posted in the chat a link that people can follow to enter in a poll to write in what your favorite asteroid is. And then hopefully that second link shows the results. But I can go ahead and share my screen while people are thinking of questions. Oh, I'm not loud, but let's see. People are entering in their choices now. So does that second link work? Can people see the results by clicking it?
Yes.
Great. So yeah, I see people are adding in. The one I get to study is their favorite asteroid. I think that's my favorite one too. We have about 13-ish minutes for any questions people want to ask, in particular of those wonderful lightning talks that we just heard from, where we didn't have the opportunity to have dedicated discussion time for those. So if you could think of any questions for the students, that would be fantastic.
Yes. So I may want to start that. I have a question for Yeji Kim. That I think if I got it right, the findings suggest fast rotator may not be monoliths, and so do you think there are other indicator would be useful to tell if a body depends, for example, on the spin rate, could be a monolith or be a rubble pile?
So for in the case of KY26, that has really fast spin speed, like 10 minutes. So our original expectation is that KY26 could be a monolithic body, but our FEM technique shows that the interior structure of KY26 is only up to 20 Pascal, and then this value is pretty, I mean, this value is observable in the rubble pile asteroid. So this indicates that we cannot neglect that KY26 could be also could be a rubble pile asteroid, which means this pressure or stress distribution can sustain the crank shape. I think you're muted.
And so does this also apply to other fast spinners that we cannot? Oh, can you hear me?
Yes, now I can hear you.
Okay. So does this apply to other fast spinner?
Yeah. This technique is also applicable to any other body that has. It doesn't matter if it has a fast spin period or lower spin period. It can be applicable to any objects. And I don't remember the specific stress range for the fast rotator, but at least the 20 Pascal was not that significantly high to cause any structure breakup or not to sustain the crank shape.
Mm-hmm. Okay, I see. Thank you.
Yeah, thank you. Thank you for your question.
All right, well, other people are thinking up questions. So Sean, I don't think we had a chance to have questions during your talk. You mentioned 3 specific processes that were involved in determining the production of the grain size distributions. Were there any processes that might be significant as well that your study just didn't include?
Yes, certainly. So I think what we try to carry out this model is to a more uniformitarian approach, that everything are rather gradual and slowly change. And of course, you could have a large impact that will change everything, that will change the local topography, and also, like it has been observed, that there are more larger boulders on the equatorial range of Bennu and Rugu, which seems to suggest the rotation, a migration of these boulders caused by rotation. And that's all these more dynamic process that is we don't have in the model. Yeah.
Gotcha. Yeah, that makes sense.
Thanks for the question.
People are feeling shy. Oh, I see a hand. Mika?
Hey. So I haven't been following this really closely here the last couple of years, but I saw a few talks that were saying that, you know, the water is being found on more and more meteorites, or I'm sorry, asteroids. And so I was wondering if the people here could have a bit more of a discussion on, so for example, for something as large as Vesta, and then so something, you know, much smaller, sort of the Bennu size, where is sort of the drawing line between what is solar wind dominated and what is either native or delivered? Is it like a distance thing or impact history? What is it that sort of determines that?
Anyone experts in this field want to comment on Mika's question?
I lost a connection for a little bit, so I didn't hear his question. Can he repeat it?
Well, sure. So my question is that where is sort of the drawing line, or sort of is it a distance, or is it an impact history sort of determiner as to whether or not the water on the surface of an asteroid is solar wind delivered or impact delivered or native?
This is Holly Besselin. I'm the teacher for Xyrus. I don't know if you're referring to our Vesta fluvial flows poster. And the person you should probably see is Jennifer Scully, Dr. Jennifer Scully. And they are for Vesta, and where this liquid, and it could have been just a transient liquid, not something that is there all the time. Could have been from the impact, but she's been doing a lot of studies, and they've been doing a lot of simulations at JPL. And she's been doing some presentations and some papers on that. And she'd probably be the one to follow up on with where this liquid's probably coming. And they're assuming it's water, but because it's the most common liquid, but she's been running through a lot of simulations on where that could have come from. And she's up to talking about it. I don't think she's at this conference though. Did that answer your question a little?
Oh, yeah. I mean, so not only just the big amounts of water, but also the small amounts of the spectral water, right?
Yeah. The only place it looked like is there are some minerals, hydrous minerals, that they say, well, maybe if there's an impact, could have done something to create some sort of a liquid, or it could have been buried from a comet or other asteroid impacts. But yeah, that's something she's been working on quite a bit, because that's kind of like the big unknown, is like, where did it come from? And even if it was just transient in nature, and under what conditions would it have been stable? So, but she's been working on it.
Micah, let me contribute a little bit. I think it's a very good question, and the answer is more complex than we would have anticipated. In the case of Bennu, we have a very strong 2.7 micron feature indicating a lot of hydrated minerals. In the case, and we have, by the way, no structural evidence for any water flow on the surface of the asteroid. It's in the case of Ryugu, its 2.7 micron feature was a lot less deep. However, I understand that the Hayabusa 2 team, and other people can speak to that in this group, has determined that the abundance of water in the samples that have been returned is actually quite high. So something was obscuring the depth of that feature on Ryugu, not on Bennu. And but we'll find out when we get both of the samples back, their relative abundances of hydrated minerals. And then your broader question of what is solar wind implanted, what is delivered by exogenous impacts like on Vesta, it's that there's a lot more work to be done there.
That's great. Thank you both so much for those great answers.
If I may add,
we also,
as far as our research
yes, please.
The traces of transient liquid, if it could be water, then we believe that there is a possibility that it could have been delivered by historic impacts that Vesta did have. And so that is also a possibility.
Great, thank you.
All right, great. Yeah, it's fantastic discussion there. Very complex topic. So we have time for one more question. I see a question in the chat for Joe DiMartini. Olga asks, is it possible in the model not only to shake the volume with aggregates, but also to spin it up to assess the influence of centrifugal force on such boulders?
Yeah, so spin-up simulations are definitely something we can do in PKD-Grav. You could look at recent work by Yun Zhang out of the University of Nice, working with Patrick Michel. There's also a lot of work going back, I think, like a decade on spin-up simulations with PKD-Grav. That said, I don't think it will have a large influence on the Brazil nut effect. Because the role of the centrifugal force is basically just to weaken the gravitational, the ambient gravitational force, right? So I'm looking at a really small patch. It was like 10 centimeters by 10 centimeters on the side. And the centrifugal force basically pushing outward against the gravitational force normal to the patch. So essentially it would probably just work to strengthen the Froude number of any given shake or oscillation that we're giving to the medium. I don't think that it would work to actually move the boulders up, except over very long time scales. Now, whether that time scale is similar to the time scale that we would need for impacts to move the boulder up, that's something I don't know yet, but it is something that I plan to look at as we progress with this research further and further. Thank you for asking that question. It's a good one.
All right. Thank you, Joe. And we're just about out of time here. So I'd like to thank all of our fantastic speakers today, as well as the conference organizers for making this all possible, and all of our attendees for joining in and asking some fantastic questions. And I hope you all were able to see what some of these favorite asteroid results were from the Mentee poll. And please come by the poster session tomorrow at 10 a.m. Pacific time. And I hope to see some of you there as well. So thanks again, everybody.
Yeah, thank you, Stephanie. Thank you, everyone.
Thank you.
Thank you, Mike.
And thank you, Mike.